This is Spacetime, Series 26, Episode 73. Coming up on Spacetime, key building blocks of life found on the Saturnian moon Enceladus, discovery of a supernova from one of the universe's first stars, and understanding how planet Earth's core was formed. All that and more coming up on Spacetime.
Welcome to Spacetime with Stuart Gary.
The search for extraterrestrial life in our solar system just got a whole lot more exciting, with scientists discovering phosphorus, a key building block of life, in the waters jetting out of the Saturnian ice moon Enceladus. A report in the journal Nature says the chemical was discovered in data from NASA's Cassini mission, which explored the Saturnian system for more than 13 years. Scientists detected phosphorus in the form of phosphates, which appear to have originated from Enceladus's global subsurface liquid water ocean. One of the study's authors, Christopher Glein from the Southwest Research Institute in San Antonio, Texas, says geochemical modeling was used last year to predict that phosphorus should be abundant in the Enceladian Ocean. Abundant levels of phosphorus were discovered in plumes of ice samples spraying out of the ice moon's South Pole tiger stripes. The Cassini spacecraft discovered Enceladus's subsurface liquid water ocean early in its mission. Mission managers then quickly changed the spacecraft's plans so it could spend more time analyzing samples in the plumes of ice grains and gases in geysers blasting out of cracks in the moon's icy surface. Analysis of a class of ice-rich grains from Cassini's cosmic dust analyzer showed the presence of sodium phosphates. The team's observational results, together with laboratory analog experiments, now suggest that phosphorus is readily available in the Enceladian Ocean as phosphates. And that's important because phosphorus in the form of phosphates is vital for life on Earth. It's essential for the creation of DNA and RNA, for energy-carrying molecules, for cell membranes. In animals, it's important for bones and teeth, and it's even present in the sea's microbiome of plankton. Put simply, life as we know it would not be possible without phosphates. Glein says the phosphate concentrations were found to be at least 100 times higher in the moon's plume-forming ocean waters than in Earth's oceans. He says using a model to predict the presence of phosphates is one thing, but then actually finding the evidence for phosphates was incredibly exciting. He's described it as a stunning result for astrobiology and a major step forward in science's search for life beyond Earth. One of the most profound discoveries in planetary science in the last quarter of a century is that worlds with oceans beneath a surface layer of ice are common in our solar system. These worlds include the icy moons of the giant planets, such as Jupiter's Europa, Callisto, and Ganymede, as well as the Saturnian moons Enceladus and Titan, and in more distant bodies like Pluto. Worlds like Earth with surface oceans need to reside in a narrow range of distances from their host stars, the so-called habitable zone, where atmospheres and surface temperatures support the pooling of liquid water on the surface. But interior ocean worlds can occur over a much wider range of distances, thereby greatly expanding the number of habitable worlds that are likely to exist across the galaxy. Geochemical experiments and modeling show that such high phosphate concentrations result from enhanced phosphate mineral solubility in Enceladus, and possibly also in other icy ocean worlds right across the solar system. Glein says that with this finding, the oceans of Enceladus are now known to satisfy what is generally considered to be the strictest requirement for life. He says the next step's clear. We need to go back to Enceladus to see if its habitable ocean is actually inhabited. That will be the most monumental achievement of science since the birth of humanity. You see, if we find life on Mars, well, that'll be a great achievement. But the Earth and Mars have been swapping rocks for billions of years, so it's possible we contaminated them or they contaminated us. We may be Martians. But if life's found in the oceans of Enceladus or places like that, places which are simply unlikely to have any contact with Earth, it means life can get started anywhere. And that has the most profound implications. This is Space Time. Still to come, discovery of a supernova from one of the universe's first stars. And a new study tries to understand how planet Earth's core likely formed. All that and more still to come on Space Time. Astronomers have just made an important discovery in their quest to better understand the very first stars in the universe. They've found the chemical signatures confirming the existence of these stars. The universe's very first stars are thought to be unlike anything in the cosmos today. You see, when the universe began 13.82 billion years ago, the Big Bang, as it's called, produced only two basic elements, hydrogen and helium, with only very trace amounts of lithium and beryllium. Eventually, these dense clouds of hydrogen and helium, which is all there was in the universe, began cooling sufficiently to collapse under their own gravity and create the very first ever stars. It was an important moment in the universe's history because it ended the cosmic dark ages by bringing in the cosmic dawn, the first light, if you will. And with it, the epoch of reionization, which would eventually give us the universe we see around us today. But the details of these very first stars remains a mystery. As I mentioned earlier, we know they were made out of virtually pure hydrogen and helium, because that's all there was. And we know that they produced all the other elements in the universe, either during their lives or when they died. Today's stars look the way they do because they contain small amounts of elements other than just hydrogen and helium. Now, astronomers refer to these other elements as metals, and by measuring the chemical composition or metallicity of a star, they can tell a lot about its evolution, its age, and even its origins. But science knows very little about that first generation of stars, not even its size. Although speculation suggests that they would have been massive, tens to hundreds of times bigger than stars like our Sun. Major efforts are now underway to learn more about these ancient ancestors, using equipment like NASA's James Webb Space Telescope and Australia's Square Kilometre Array and Sky Mapper projects. Physics tells us that when really massive stars, those maybe 140 to 260 times the mass of our Sun, go supernova at the end of their lives, they generate an unusual type of core collapse supernova called a pair instability supernova. And these would have left a very unique chemical signature in the atmosphere of the next generation of stars, a signature that's quite unlike that of other supernovae. The problem is, there's been no sign of this signature in ancient supernova remnants, at least not until now. Now, a new report in the journal Nature outlines the first definitive association of a galactic halo star, that's a star that's really old, with an abundance pattern originating from a pair instability supernova. One of the study's authors, Professor Alexander Hedger from Monash University, says the chemically peculiar star Lamos J1010 plus 2358, located in the galactic halo, is clear evidence of pair instability supernovae from very massive first stars in the early universe. This unique supernova type is due to a hydrodynamic instability caused by electron-positron pair formation at the very end of the massive star's life. Pair instability supernovae disrupt the entire star, meaning unlike other core collapse supernovae, which can leave a neutron star, they leave no remnant. A pair instability supernova explosion can be anything from a few times to hundreds of times more powerful than a normal supernova, and the explosion that made J1010 plus 2358 was among the most energetic pair instability supernovae. The study found that the most likely progenitor for the star J1010 plus 2358 was a 260 solar mass pair instability supernova. Hedges says the work provides an essential clue for constraining the initial mass function of stars in the early universe. He says that prior to this study, there was no evidence of pair instability supernovae in the first stellar generation. But using the Subaru telescope, Hedger and colleagues conducted a follow-up high-resolution spectrographic observation focusing on J1010 plus 2358. From this, they found and calculated the abundances of more than 10 elements. They showed that the star had low sodium and cobalt abundances. In fact, its sodium to iron ratio is less than 1 in 100 times that of the Sun. The star also has a big difference in the abundance of elements with odd and even charge numbers, like sodium, magnesium, cobalt, and nickel. Now that's a pattern Hedger says is unique to pair instability supernovae. He says the peculiar odd-even variants, along with deficiencies in sodium and alpha elements in the star, are all consistent with the predicted chemical fingerprint of primordial pair instability supernovae from first-generation stars with 260 solar masses. The authors also found that the iron-to-hydrogen abundance in Lamos J1010 plus 2358 was 2.42, substantially greater than the most metal-poor stars in the galactic halo, suggesting that second-generation stars created in the gas dominated by pair instability supernovae ashes can still be quite metal-rich. Hedger thinks that J1010 plus 2358 may in fact be the oldest star we know. Because they're really massive and burn through their nuclear fuel supplies really quickly, the stars that make pair instability supernovae have the shortest lifespans, and the metal-rich gas they make can be used to form the next generation of stars. Hedger says the identification of such a massive primordial star suggests that the first stars would have been more massive than the stars forming in the present universe, and this confirms why we've never found a long-lived low-mass primordial star. Pair instability supernovae were first hypothesized more than 80 years ago. They're the only type of supernovae which scientists believe they fully understand the workings of. Yet they're also the only type which scientists have never uniquely identified before. So this discovery is an important cornerstone in science's understanding of how massive stars explode. Pair instability supernovae also play a crucial role in astronomy's understanding of the birth masses of black holes, and they determine what gravitational wave signals we can observe from black hole mergers. Hedger says J1010 plus 2358 confirms the existence of primordial stars of several hundred solar masses for the very first time. Stars in this mass range end their lives as black holes, capable of swallowing up the entire mass of the star instead of it exploding. In fact, he says they may be the first stellar mass black holes in the universe.
Yeah, so the universe started off with just hydrogen, helium after the Big Bang, and then all the metals after that were made by stars in subsequent generation of stars. So one generation lived, exploded, and then a next generation of stars formed. And so now astronomers classify these stars in terms of populations, and due to some history to this, we call population 1 that are the dominant population in our galaxy, stars that form around our age, similar to our sun, so that form within the last few billion years. And then there's some older generation of stars that has been discovered, and that are called population 2 stars. But then there's also a hypothetical population of stars, which has been the very first generation that formed out of the pristine primordial matter that was made in the Big Bang directly, where there was no initial stellar enrichment, and this is called the population 3 of stars. And these have initially no metals at all, or no heavy elements, no elements heavier than hydrogen or helium, which astronomers generally call metals. So there has been this kind of generation because we know the Big Bang has not made these heavy elements, but only hydrogen, helium, and so those stars made of the pristine material are called population 3, but then there is a property of stars that the bigger they are, the shorter they live. And only stars that are less than about 80% the mass of the sun, they can live as long as the age of the universe. And so in principle, if there were any of stars that were less massive than 0.8 solar masses when they were born, even if they were born as the first generation, they would have lived as long as the age of the universe. So we would see them today, but we have never found one of those stars directly. So we know they have existed, but we haven't seen any of these smaller mass stars. So generally it's thought that this first generation of stars also were largely made of stars that were larger, bigger than 0.8 solar masses, whereas in the present day in the universe, when we look, the dominant population of stars are about the mass of the sun or less. And so we know that the first generation probably was very different than what we see today.
And that's because they were formed in a different way.
Yes.
Virtually pure hydrogen and helium, maybe trace amounts of lithium and beryllium, but that's it. When you look for these stars, although none are in existence today, there would be telltale signatures which you'd find in the atmospheres of, say, population 2 stars.
Yeah, so that is the trick now is observationally. So since at present we can't, but when this first generation of stars formed, this was only a few hundred, maybe less than 1 billion years after the Big Bang. So all of these bigger stars would be gone. And so the only way for us to see anything of them, if you can't see the stars directly, is from their ashes. So when they exploded and then make a next generation of stars, which, as you said, is population 3. We call population 3. So any kind of stars that are very old and not population 3. So they would form from the ashes. And if they were polluted only by one or a few of these supernova, then the material from this earlier supernova explosion would have made this next generation of stars. And if they are low enough in mass, they live until the present day. And this is where we can see it. And we can see in the atmosphere of these stars the material that came from the stars, that the one generation of stars, population 3 stars that lived before them, and made these elements. And because depending on how massive stars are, when they die, they produce a very unique signature of elements, a ratio of elements relative to each other, kind of like a chemical fingerprint, if you like. And that is what we can observe and then inverse that and say, okay, if we see this kind of signature, we know what kind of star must have exploded.
And so what you're looking for is a very specific type of core collapse supernovae called a pair instability supernovae. What does that mean?
So there is depending on mass of the stars, they can end their lives in different ways. So stars below somewhere around 8 to 10 solar masses, they will end their lives as a planetary nebula and leave behind a white dwarf. And if the stars get somewhat more massive, they start making so-called core collapse supernova, and those make a neutron star, or in some cases when a mass of the star gets larger, they will collapse and make black holes, and in some cases supernova or not, or other spectacular deaths. But if the mass of the star gets large enough, somewhere above 140 solar masses initially, when those stars die, they explode in a very spectacular supernova called pair instability supernova, electron-positron pair instability supernova. This is because of some property of the equation of state that the temperature inside the star is very high and the density is very low, and they can make pairs of electrons and positrons. So the positron is the antiparticle of the electron. And that changes how compressible the gas is, and the star can actually, the pressure can no longer sustain against the gravity, and the star contracts rapidly and then does very rapid thermonuclear burning and then explodes in a spectacular explosion.
And this leaves a very specific chemical signature, and that's what your work's found.
Yes, these kind of supernovae, when they explode, they make a very peculiar abundance pattern that has much more elements that have an even charge number, so like oxygen, magnesium, and much less of these elements that have an odd charge number like sodium or aluminum. And this is particularly strong, the signature, when such a pair instability supernova goes off from population 3, because there are no initial metals, and that is what turns out it affects how strong this odd even pattern is that we will see in the signature. And it's a very unique signature. We have been looking for that, to see this in any kind of star for a long time, because it was a very clear signature. And in contrast to all other kind of supernovae, these pair instability supernovae, we actually understand how they work extremely well. And so predicting the signatures was sort of straightforward, unique, and yet it had never been found. And that was really a big puzzle for a long time.
And now you found it. Tell me about it all.
Yes, and so there was now one star that has been found called J1010 plus 2358, and so it was found by the Lamoste telescope that's sitting in China, close to Beijing. And so they identify stars and do follow-ups with a more powerful telescope, Subaru telescope, and then they analyze the spectra of the star and extract from that information about the abundance of the elements, or particularly the relative abundance of the elements that is in the atmosphere of that star. One very interesting thing is that in the past, people have largely looked at stars that have extremely low metallicity as the oldest stars in the universe. And that is because we know that after Big Bang, there was this pure material, and then successively the universe was more and more enriched in metals in the ashes from subsequent supernovae. So we stay polluted with metals. All these heavier things is basically just the waste product of stars, also we are made of mostly. And so it's very clear that when you find a star that has extremely low metallicity, it must have formed very early in the universe, very soon after population 3. And so this was kind of an easy identification. Also know that when a supernova goes off, they actually can make a lot of metals. In particular, parent Cybele supernovae, they are really big stars, and when they explode, they leave no remnant behind, so no neutron star or no black hole that would swallow all of these ashes, waste products of the stars, but everything is expelled and make a vast amount of metals, so 100 solar masses of them. And you would expect that with so much metals, you don't pollute things just a little bit, but you can actually pollute it by a lot more when this explosion goes off. And so the prediction was there might be a lot of stars that have that signature, but they are not that low in metallicity, but somewhat higher in metallicity as well. But the problem now is that in our galaxy, there's many, many stars of higher metallicity, and only these low metallicity stars that are very rare, that they easily stick out and can be analyzed as old objects. But the other ones have many similarities if you don't look in much detail to many of the stars that sit in our galaxy. And so finding one of those with a particular signature, you have to look very closely, and it's like finding a needle in a haystack, literally a very big haystack, because there's 100 billion stars in our galaxy. And so this was really remarkable to find now one of those stars that is somewhat higher enriched than the low metallicity object or ultra low metallicity object we usually identify with the first generation or the ashes from the first generation, but now show the signature and not being at very low metallicity but at higher metallicity as it has been predicted by theory. And this is really remarkable to see that signature also with this high enrichment level that corresponds to having actually one of these parent Cybele supernovae that produces lots of metals in one spot.
It's not the first time we've seen evidence of parent stability supernovae.
Well, there have been a few light curves that have been sort of associated with it, but not all of them were, actually none of them was really unique. Often that had been revised, that there may have been other counterparts. So none of these are as much of a smoking gun than finding the chemical signature.
Yeah, the difference is this time we're looking at the progenitor being a population 3 star.
Right, and so most of the light curves that we see, these are stars that live in our current universe, so they're much more metal rich, and so this is the other aspect, that it's not just absolutely a smoking gun for a parent Cybele, but also that it had to be top 3 parent Cybele that had to make that signature.
It's a stunning discovery. What are its implications?
Yeah, so the implication is that we didn't know, we still don't know exactly what the initial mass function is. So how many stars of what mass do you make in the first generation? What typical masses of the first generation? I mentioned at the beginning that there were probably not a lot of population 3 stars had below 0.8 solar masses, because they would have lived as long as the age of the universe and they would still be around, but we have never found one. So we know they probably were more massive, but we don't know how massive they were, whether they were all about 50 solar masses or around 20 typically. But now we have found this object, which had to come from a star that was probably at least 250 solar masses when it was born. So we know that most likely have been very massive stars in the early universe, and the stars around that mass, a little bit more massive than what was the progenitor of this object, they would not have exploded, but they would have made a black hole. So there is implied also that we should expect to see black holes of a few hundred solar masses being born in this first generation of stars. So it gives us a very good indication that what the typical mass scale of the first generation may have been, or at least that there have been some of these stars that were that massive of hundreds of solar masses. Very important to know.
That's Professor Alexander Hedger from Monash University. And this is Space Time. Still to come, understanding how planet Earth's core formed, and later in the science report, new questions of ethics raised as scientists use stem cells to create cloned synthetic human embryos. All that and more still to come on Space Time. Scientists have developed new techniques to provide fresh insights into the differentiation of planet Earth. The findings, reported in the journal Science Advances, were developed by Carnegie University researchers Yinghui Fi and Ling Wang. They provide fresh insights into the processes by which the dense materials that form the Earth's core descended into the depths of the planet, leaving behind geochemical traces that have long mystified scientists. Like everything else in our solar system, planet Earth accreted from the protoplanetary disk of gas and dust that surrounded the early nascent Sun 4.6 billion years ago. As the Earth grew from collisions of smaller objects over time, the densest materials sank inwards, separating the planet into distinct layers, including an iron-nickel-rich metallic core and a silicate mantle. Fee says the segregation of the core and mantle was the most important event in the geologic history of the Earth. That's because it allowed for convection in the liquid metal outer core of the planet, and that convection powers the Earth's magnetic field, which shields the planet and life on it from cosmic rays and irradiation from the Sun. Without it, life as we know it simply couldn't exist. Each of the Earth's layers has its own unique composition. Although the Earth's core is predominantly iron and nickel, seismic data indicates that some lighter elements, like oxygen, sulfur, silicon and carbon, were dissolved into it and so brought along for the ride to the planet's centre. Likewise, the mantle is predominantly silicate, but its concentrations of so-called iron-loving or siderophile elements have mystified scientists for decades. Understanding the mechanisms by which materials migrated through these layers and identifying any remnants of this process will improve science's understanding of the ways in which the Earth's core and mantle have interacted throughout the planet's history. To do this, the authors used heavy hydraulic presses, just like the ones used to make synthetic diamonds, in order to bring samples of material to high pressures and temperatures, mimicking the sort of conditions found in the Earth's interior. And this enabled them to recreate the Earth's differentiation process in miniature and to probe different possible ways by which the core was formed. Using these tools, Wang and Fee developed a new method for tracing the movement of the core forming liquid metal in their sample as it migrated inwards. They showed that much like water filtering through coffee grounds, under the dynamic conditions found on early Earth, iron melts could have passed through the cracks between a layer of solid silicate crystals called a grain boundary, and in the process exchanged chemical elements. Wang and Fee suggest that the violent environment of the early Earth would have actually created the circumstances that could have turned the mantle into a sort of giant pour-over coffee apparatus, allowing the percolation of liquid metal through an interconnected network. They analysed the chemical exchanges during this percolation process and found their results would account for iron-loving elements being left behind in the mantle, shedding light on a long-standing geochemistry question. Looking ahead, the authors believe their new technique is also applicable to other rocky planets and will help answer more questions about the core-mantle interactions occurring deep in their interiors. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with a science report. The annual meeting of the International Society for Stem Cell Research has been told that scientists have used stem cells to create cloned synthetic human embryos, thereby sidestepping the need for eggs or sperm. The historic announcement raises many ethical questions and will likely lead to further debate about the so-called 14-day rule, which is the current legal limit for using embryos or embryo-like structures for research purposes. Professor Rachel Ankeny from the University of Adelaide, who was not involved in the project, says it's important to develop a much deeper understanding of the earliest stages of human development, especially as these are essential for developing better clinical responses to things like infertility, miscarriages, and developmental errors. However, researchers also need to consider whether these sorts of models, if in fact that's what they are really all that fundamentally different from human embryos. Although they originate from different sources and processes, they have the same characteristics as real human embryos, which makes the issue about how science will view and treat them much more complex. Back in 2022, the Australian National Health and Medical Research Council regulator licensed Monash University scientists to develop a similar novel being, which they called an iblastoid. These lack the ability to be implanted into a uterus and develop full term. But the regulator ultimately determined that iblastoids did meet the definition of a human embryo and were therefore subjected to existing laws on human embryo research. A new report has shown that 3 scientists conducting gain-of-function research at the Wuhan Institute of Virology were the first ever humans to contract COVID-19. The findings have been published on the Substack newsletter Public by respected investigative journalists Michael Schellenberger and Matt Tabai. The new findings identified several patient zeros, or is that patient zero, including Ben Hu, Ping Yu, and Yan Zhu, who were all scientists at the Wuhan Institute of Virology when they suddenly became ill around September 2019. Importantly, the 3 were researching gain-of-function experiments with SARS-CoV-2 viruses. Gain-of-function experiments are designed to increase a virus's infectiveness, making the pathogen stronger, and thereby allowing scientists to better understand the sorts of threats they're likely to pose in the future. But it's important that world's best practice biological containment facilities are used to prevent these deadly viruses from escaping into the real world. They followed the release of an independent investigation by the US Department of Energy in February, which confirmed earlier findings by the FBI that COVID-19 originated from an accidental outbreak at the Wuhan Institute of Virology. The US State Department had also previously acknowledged suspicions that the COVID pandemic may have originated from a lab leak at Wuhan. The now archived State Department report, published on January 15, 2021, states that the US government has reason to believe that several researchers inside the Wuhan Institute of Virology became sick in the autumn of 2019 with symptoms consistent with COVID-19. Almost 7 million people have now been killed by the COVID-19 coronavirus. However, the World Health Organization estimates the true death toll is likely to be around 18 million, with some 768 million confirmed cases globally, and that's almost 10% of the world's population. Scientists have detected the first virgin birth in crocodiles. A report in the journal Biology Letters examined the DNA of an American crocodile mother who lived an isolated life and 12 of her eggs, and found that a fully formed fetus in one egg was genetically identical to the mother, suggesting it had developed without the egg being fertilized by a male crocodile. This type of reproduction, called facultative parthenogenesis, is known to occur in several species of fish, lizards and snakes, but it's not been known in crocodiles before now. Although the eggs didn't hatch, scientists say it's possible that now extinct relatives of crocodiles, and that includes dinosaurs, could have reproduced in just this way. There are growing concerns among science-based medical practitioners that the World Health Organization is validating debunked pseudoscientific practices. The Constitution of the WHO clearly outlines its principles, namely that enjoyment of the highest standard of health is a fundamental human right, and that unequal promotion of health and control of diseases in different countries is a danger. Basically, it means health for all, regardless of race, beliefs, or socioeconomic condition. The problem is, since May 2013, the World Health Organization began following a traditional medicine strategy, some would say akin to witch doctors, in which science plays no role. Tim Mendham from Australian Skeptics says what the WHO sees in traditional and complementary practices such as Ayurveda, traditional Chinese medicine and naturopathy is an easy way to fulfill a goal by simply acknowledging the presence of healers of various types with little attention given to the kind of care they're providing.
Recent actions by the WHO in certain areas has really tarnished its reputation. I mean, it was doing good things, and it still does good things, right? Vaccinations and treatments for all sorts of diseases and the general health of people. So, great work, but it's heavily funded by nations and apparently by China, especially. Some areas, it certainly seems to be leaning pro-China and pro-China's policy, as the case with the COVID investigations. They might have been pretty naive in going and expecting Chinese to be open with them, but also in the fact of pushing traditional Chinese medicine. This is something that's been happening in a number of places actually around the world, that there's a soft diplomacy attitude of China has been to promote traditional Chinese medicine, which relies a lot on herbal animal products, obviously, rhino horn and that sort of stuff, and some very, very strange medical diagnoses, often involving qi, which is just an energy form that runs through your body, supposedly, and it's very unproven. The story goes that after the revolution in China that brought in the Communist Party, Chairman Mao realised there weren't enough proper medical facilities around, they here encourage this use of these sort of folk cures, if you like, of traditional Chinese medicine. So now the WHO seems to be sort of promoting a lot of these cures. They refer to things like the diagnosis that the liver qi stagnation, whatever that means, is an issue, and that fire-harassing heart-spirit pattern is another diagnosis. And the same thing has happened in Australia too, by the way. They're actually allowing a lot of these very esoteric and abstract and, quite frankly, sort of unfounded diagnoses and of prognoses, if you like, of people's conditions based on completely out there belief systems, which is totally unfounded. And this is the TGA.
We'll see the same thing with traditional Indian medicine soon too.
Traditional Indian medicine is creeping in. Ayurveda stuff.
Yes.
It's creeping in Australia, and that's being pushed heavily by the Indian government. In fact, they've got a department of Ayurveda, actually, I think, who are pushing there, obviously trying to sort of tap into that market, the folk cure market that the Chinese have got a lot of, and the Indians sort of pushing the same thing outside of their own population. Story goes, if 1 billion Chinese are using this traditional Chinese medicine, it must be good. Nope, not necessarily. It could just be a folk cure that's been around for a long time and hasn't changed and still doesn't have much of a foundation. The same with a lot of Ayurveda stuff from India. And there's a lot of other folk cures around the world, obviously, which they'd all love to be sort of pushed by the WHO because it helps them make a bit of money. So it's a sad thing with the WHO sort of, while doing good stuff, is also doing bad stuff.
That's Tim Mendham from Australian Skeptics. And that's the show for now. Spacetime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. Spacetime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the Spacetime store for a range of promotional merchandising goodies, or by becoming a Spacetime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more Spacetime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our Spacetime YouTube channel, and on Facebook, just go to facebook.com/Spacetime with Stuart Gary. And Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.